Hello everyone, my name is Minoru GOTO. I'd like to introduce nuclear design study of innovative reactors. First, let me introduce myself. After graduating from Tokyo University of Science, I worked at Sumitomo Atomic Energy Industries for 10 years, where I was engaged in radiation shielding calculations and analysis of reprocessing of spent fuel. After that, I moved to Japan Atomic Energy Agency, where I was engaged in test planning of the HTGR, improvement of nuclear analysis method, and nuclear design of improved core for about 20 years. Previously, I was a group leader of the HTGR design group of Japan Atomic Energy Agency. This fiscal year, I moved to University of Fukui as an associate professor and started nuclear design study on innovative reactors. Next, I will briefly explain the background of innovative reactor development in Japan. Innovative reactors include SMR, HTGR, and FR. Among them, HTGRs are attracting attention for their high safety, high efficiency power generation, and carbon-free heat source for hydrogen production. In Japan's green growth strategy, through achieving carbon neutrality in 2050, which was formulated in 2021, a roadmap is described for the development of innovative reactors, including HTGRs. Therefore, we will contribute to the realization of carbon neutrality through nuclear design study on HTGRs. Next, I will give an outline of HTGR using the HTTR, which is Japan's testing HTGR, as an example. The red part in the left figure is the core, which is approximately 2.9 meter high and 2.3 meter in diameter. The core is a stacking structure of hexagonal graphite block as shown in the photograph. To achieve high temperature, HTGR uses helium gas as the coolant and graphite as the moderator. The reactor outlet coolant temperature is up to 950 degrees C, which is more than 600 degrees C higher than that of LWR. This schematic view shows fuel configuration of HTTR. The coated fuel particle is composed uranium dioxide fuel kernel and 4 layers, which are low-density pyrocarbon, high-density pyrocarbon, silicon carbide, and high-density pyrocarbon. Diameter of coated fuel particle is about 0.9 mm, and diameter of fuel kernel is about 0.6 mm. The coated fuel particles are sintered with graphite matrix to fabricate fuel compact. The fuel compact is composed 13,000 of coated fuel particles. The fuel compacts are enclosed in a graphite sleeve and a fuel rod is fabricated. The fuel rods are inserted into hexagonal graphite block and a fuel block is fabricated. 5 fuel blocks are stacked and a fuel column is constructed. HTTR core consists of 30 fuel columns. I'll explain about the HTTR core structure. The left-hand schematic view is the horizontal cross-sectional view of the core, and the right-hand one shows the bird's-eye view. In this schematic view, the region indicated in red is a fuel block. The regions indicated in gray with 3 circles is a control rod guide block. The regions indicated solid gray is a replaceable reflector block. The fuel blocks and the control rod guide blocks and the replaceable reflector blocks are the same size and are made of high purity graphite. The control rod is inserted from the top of the core through the control rod guide block to the bottom of the fuel region. The core consists of 30 fuel columns, so 150 fuel blocks are loaded into the core. I'd like to explain about the outline of nuclear design study on HDGR. We have 3 major subjects of study. First, nuclear design for high power and high burn-up. Second, nuclear design using the feature of HDGRs, such as plutonium burner and thorium utilization. And third, improvement of a nuclear calculation code system to deal with problems specific to HDGR. The calculation code used in this study are MVP, SLAC, and MCNP, which are widely used in Japan. Much of knowledge on the nuclear design of HDGR is common to LWR. Thus, the computational skill and nuclear design knowledge to be acquired through this study can be used not only for HDGR, but also for other reactor types such as LWR. Finally, a summary. HDGRs are one of the typical types of innovative reactors which are attracting attention. They are high safety, high efficiency power generation, and carbon-free heat source for hydrogen production. Nuclear design study on HDGRs contribute not only to improving the safety of nuclear power systems, but also to achieving carbon neutrality. There are 3 subjects of study, and they are nuclear design of high power and high burn-up, nuclear design using the feature of HDGR such as plutonium burner, and improvement of nuclear calculation code system. The acquired computational skill and nuclear design knowledge through this study can be used not only for HDGR, but also for other reactor types such as LWR. Thank you for your attention.